Welcome to Mahatma Education Society's e-learning channel. This is the sixth of a series of lectures on Introduction to Mechanical Vibrations. We are in the chapter Basic Concepts of Vibrations. The outline of the lecture is, we have a recapitulation of last lecture, vibration classification, steps involved in vibration analysis, and addition of harmonic motions of same frequency. The recap. So we have seen the remaining terms of vibrations in the last lecture. One point I missed out. This is the significance of simple harmonic motion. So why is the study of simple harmonic motion necessary? So we have very close approximations of practical systems occurring in nature to the simple harmonic motion. That's why simple harmonic motion study becomes very important. Secondly, the study of simple harmonic motion helps in dealing with any periodic motion, since any periodic motion can be broken down into a sum of simple harmonic motions with the help of a Fourier series. Hence, assuming that the displacements are very small, then we can convert a nonlinear system into a linear system, and we can superimpose simple harmonic motions of different frequencies into a complex periodic motion. That is the idea. All the parameters that we are going to study in this subject, we will deal with the simple harmonic motion. So be it displacement, velocity, or acceleration, or even force, the variations of all these parameters will be assumed to be simple harmonic in nature. Now we will see the brief classification of mechanical vibrations. So vibrations can be classified according to the degree of freedom. In the first case, we have seen what is meant by lumped mass system or discrete masses. So in that we are having finite degree of freedom involving single degree of freedom to start with, and then multi degree of freedom systems. Then we have the continuous parameter or distributed parameter system, where apart from the mass, the system also is having the stiffness and damping properties. So it is a case of infinite degree of freedom. So as engineers, we will try to convert this infinite degree of freedom to a lumped parameter system for analysis. The second classification is presence or absence of excitation. So if there is no excitation force or excitation displacement, then it is a case of free vibrations. We are only required to give the initial disturbance, and vibrations continue on account of the inherent parameters. Secondly, if there is the presence of continuous force from outside or in the form of displacement, then it is a case of forced vibration, which may be again periodic and non-periodic. So we are having only this periodic for our study. Damping, whether damping is there or not. So initially we will focus on undamped systems, and then we look at the damped systems. In the case of damping also, we have 4 different levels, 4 different cases, and we will look at only the viscous damping and Coulomb damping, that is the dry friction damping. The remaining damping types we are going to neglect, and they are beyond the scope of our study. Now, classification based on governing differential equation. We have the linear differential equation and non-linear differential equation. For almost all the systems that are practical in nature, they are highly non-linear. So this is not within our scope of study, and we will convert all nonlinear systems in terms of linear systems by making some assumptions or approximations. So we are going to study these linear governing differential equations. According to the nature of excitation force in case of forced vibrations. So we have deterministic vibrations and random vibrations. In the deterministic vibrations, we know the nature of the force before solving the problem, and hence the output, that is displacement as a function of time and related parameters, can also be predicted with reasonable accuracy. In case of random vibrations, we don't know the value of the force as a function of time accurately. For example, earthquakes, winds, and so on. So the exact value of force as a function of time is not known to us. So how do we analyze such kind of problems? Generally, we take the historical recordings or historical data of past earthquakes, and then we try to fit in the data using some mathematical tools such as random number generation, and we try to imitate the trend, right? So we make an approximation to the input force, and hence the output, that is the displacement, also gets approximated, and we also don't expect that this displacement as a function of time is accurate. So we get a reasonable trend of this, right? So for our study, this is not there, so we limit our scope to deterministic vibrations only. And lastly, classification based on the direction of vibration movement. So it is longitudinal or linear vibrations. The movement of the masses are in a direction along the main axis. Then torsional vibrations, movement is about the axis, and transverse vibrations, for example beams, where the movement is perpendicular to the main axis. Now, steps involved in vibration analysis. Basically there are 3 steps. The first one is mathematical modeling. It involves derivation of equations of motions, which involves abstraction with some assumptions leading to a simplified model. So the real system may be something like a bench, right? It can be something like a bench, or it can be of any different form. Now we want to study this system. So what we try to do is, we try to approximate this system by basic elements of vibration, a combination of spring, mass, and damper. So here I am showing only one of each of these quantities. So how many number of masses, how many springs, and how many dampers to be used, and whether it is translational or rotational in nature, and what is the orientation of each of these. It may be inclined also, right? So all of these has to be decided by the design engineer, and logically this schematic model should be representing the real system, right? So we also make certain approximations and abstractions out of all the parameters that are playing a role in the real system. There are only a few of these which are very important. So few parameters, they play a role, or they are very important for our study. There are some other parameters which are having least importance, and that we try to neglect it. For example, if we are dealing with large amplitudes, then if we are dealing with large amplitudes, then we come across the non-linear zone or non-linearity, right? And to solve this is a very difficult process. We get a non-linear differential equation, and which becomes very difficult to solve. Hence As engineers, again we try to convert this into a linear problem which is simple to solve. So instead of large amplitudes, I assume that we have a very small amplitudes of vibration, and which will be giving us the linear differential equation, which then becomes easy to solve, right. So we will come across some terms, sinusoidal terms such as sine and cosine, for example in simple pendulum, right. So these are non-linear in nature. So we try to remove these and instead assume some other parameter in terms of the coordinates, so that a non-linear system becomes linear, right. So now this is the simplified model, and that will be a representation of the real system, right. So I can get n number of such models created with different degrees of freedom. So as a design engineer, to start with any problem, I start with a schematic model having the least degrees of freedom. Say it is only 1, something like this. So only one mass represents all the masses in the real system. Only one spring represents all the elastic components in the real system, and only one damper represents all the damping coefficients or dissipating elements in case of the real system. So what is the advantage in this one? What is the advantage? So when I solve this, I get some value of omega n, right, and this will be very crude, or there will be a lot of error when involved, but I get a decent approximation, or I get a fair idea of the range of lowest omega n. In this case, I am having only 1 degree of freedom in the schematic model, so I will expect only one value of omega n. But if the real system is experimented with, and which might consist of n number of degrees of freedom in real system, so we can sort that in increasing order, omega n1, omega n2 likewise. Okay. So this single omega n for a schematic model for 1 degree of freedom can be compared with the lowest omega n for the real system by doing some simulation using some software, and we get lot of error. But the positive point here is that I get a fair idea about the range of omega n that is possible with this. So in the next stage or in the next iteration, you can increase the number of elements. You can increase the number of elements. It is m1, m2 likewise. Okay, even you can have something more over here, m3, and it's up to the design engineer to create another schematic model. So this will be having a degree of freedom somewhat more than the earlier one. So this is another schematic model having a more number of degrees of freedom, and in this case again I will be having number of omega n's depending on the degree of freedom of the schematic model, and in this case I can expect that the least omega n, the fundamental frequency or the basic frequency of this schematic model, will be much more accurate than the earlier one compared with this for the real system, right. But still, if you are not happy with the results, you can further increase the degrees of freedom in the third model. So likewise, I can have n number of iterations, and each iteration has increasing values of degrees of freedom so as to get greater accuracy in our answers. But the negative point over here is, for increasing accuracy, we are dealing with increased degrees of freedom for each schematic model, and hence there will be that many number of differential equations which becomes more complex to solve. So it's a trade-off or compromise for the design engineer between the accuracy required and the computational requirements, right. Now the second step involved in vibration analysis is the solution of mathematical equations and analysis. So I forgot to tell one thing about the mathematical modeling. After creation of the mathematical model, the schematic model, you are required to create free body diagrams and then get the differential equations of motions which are required to be solved. And we are now into the step number 2, that is the solution of equations. So, using mathematical methods such as matrices, we are going to solve a system of n number of differential equations, right, so as to get the values of natural frequencies which will be sorted out and the mode shapes, right. So, even we can get the values of the displacements as a function of time for different masses, right. So, we primarily deal with these two parameters. So, we have the concept of these eigenvalues and eigenvectors. So, these come into number of areas in mathematics, particularly this will be, these tools are used when I have multiple solutions to any given problem. So, I cannot say that the system is having only one solution, I can have multiple solutions possible. So, eigenvalues gives us a fair idea about the natural frequency. In fact, mathematically or technically, these eigenvalues are denoted by lambdas, so which are nothing but the square of the natural frequency, right. So, once I get lambdas for the given problem, I can take the root of that so as to get the value of omega n, which are then sorted out in increasing order. Likewise, I will be getting omega n1, omega n2, likewise. So, the least one is the omega n1, that is the most important. Eigenvectors give us an idea about the mode shapes, the configuration attained by the bodies or the system when they are vibrating with any one natural frequency. So, we are talking about the resonance conditions. Now, the last step is also very important. Based on the output that we have got, then we have to interpret the solution, right. So, whether or not these values obtained after solution are acceptable to me or not, right. I may have a lot of deformations of the elastic members, so which may not be practically feasible. So, deformation is one of the criteria of failure, and to select whether the design is good or bad. So, I need to talk with respect to deformations. Other one is because of deformations I am having the stresses induced. So, the stresses, if they are going beyond the permissible stress for the material, then also I can say that the material is failing. So, I am having these two criteria, right. So, failure criteria. So, based on these values in the solution step number 2, I am going to check for the deformations and the stresses and check whether they are okay or not. If it is okay, then we will apply that for the further process, right. And if it is not okay, then we can make changes in the design, something like changes in dimensions. If not okay, then changes in dimensions, or you can have changes in the material likewise, or in the parameter, fine. So, this completes the 3 steps of the vibration analysis. Now, the next point is how do you add harmonic motions of the same frequency, right. The occurrence of one of the motions is different than the occurrence of the other. So, let us assume that I am having one motion. So, I am taking the rotating vector form. Let us have this as amplitude A1 of the first motion, and this is inclined at angle theta, that is omega t. This is the reference axis from where I am going to measure the time. These are the actual values of the parameters in y axis, right. So, I can define x of t or x1 of t for the first motion as A1 sin omega t. So, we are taking the projection of this particle or of this vector along the ordinate. So the distance from here to here will be x1, a function of time, the actual value. Likewise, let us say that x2 is leading the x1 by a phase difference of phi. So it is a2 sine of omega t plus, let us call this difference as phi. So a2 is somewhere like this, right, and this is angle phi. So I say that a2 is leading the a1 motion by an angle of phi. So both are rotating anticlockwise synchronously and both are having the same speed. So for any given instant of time, both are having the phase difference of phi. a2 leads a1 by angle phi. So if I am having leading, I am having plus over here. If it is lagging, then I will say I am having minus, right. Now I want to add both of these motions and see what is the final motion like. So let us see the final or resultant motion. Displacement x of t is equal to x1 plus x2 of t. So I can add both of them, a1 sine of omega t plus a2 sine omega t plus phi. Now expand a1 sine of omega t plus, so this is sine a plus b is sine a cos b plus cos a sine b. So it is sine a cos b plus cos a sine b. Now you take the sine of omega t as common thing, right, sine of omega t multiplied by a1 plus a2 cos of phi plus, I will write here cos of omega t multiplied by a2 into sine of phi. Now let me write, instead of these parameters, underlined ones, replaced by different parameters. So let us go back to the rotating vector form. So what is a1 plus a2 cos phi? So a1 is directed in this direction. I am trying to add something more in the same direction, that is a2 into cos of phi. So what I am trying to do is I am trying to do a vector addition now. So if I am having a number of vectors, I need to join them end to end in the same order. So this can be the starting point of the second vector can be taken as starting from here, right, something like this. So it can be called as a2 and this angle is phi. So I am having the projection of this onto this line, right. So this amount is equal to a2 into cos of phi. So basically this value is equal to a1 plus a2 cos of phi, and I get the resultant from the vector addition of these. Let us call it as resultant as a, amplitude a, right. So it is a into, what is that, let us call this as alpha. The resultant makes an angle of alpha with the first vector. So it becomes a multiplied by cos alpha, that is a1 plus a2 cos phi, and remaining is sine of omega t plus cos omega t multiplied by a2 sine of phi. So a2 sine of phi is this thing, a2 sine of phi, which also is equal to a times sine of alpha, right. a2 sine phi is equal to a sine alpha. So a sine of alpha. Now separate out the a, that is common thing, and you are having sin omega t cos alpha and cos omega t sin alpha. So it is a multiplied by addition of these two products, which is sin of omega t plus alpha. So what is the result here? When I add any two motions, or it can be a multiple of harmonic motions but having the same frequency, then I have a resultant having some amplitude but rotating also with the same frequency. I am having a omega, right. So I can find the value of alpha here, that is tan inverse of A2 sine of phi divided by A1 plus A2 cos of phi, right. So, what we have seen is why the simple harmonic motion is important for our study. Then we saw what is how the vibrations are classified. Then we saw the steps involved in vibration analysis, the 3 basic steps, right. And finally, we saw how to add 2 harmonic motions of the same frequency, so that we get a resultant motion which is also is a simple harmonic with the same frequency. Hope you understood the concepts. Thank you.